In this video, we'll learn about climate change, greenhouse gas emissions, and how home energy inspections are good for our homes and for our planet. Our atmosphere is just a thin layer of gases surrounding our planet. It absorbs solar radiation, it retains heat to warm the Earth's surface, and it's a delicate mixture of gases separating life on Earth from the rest of the cosmos. But when this mixture of gases gets out of balance, the temperature rises and alters our climate. Carbon is an essential component of Earth's atmosphere, but it's also the primary driver of our warming climate. We are learning more about our changing climate by studying how carbon dioxide, CO2, moves through the atmosphere, the ocean, and plant life. Every year, human activity is responsible for approximately 8 billion metric tons of carbon released into the atmosphere. 1 ton of carbon would be the equivalent of, say, a small convertible sports car. Now, 8 billion of those cars are put into the atmosphere every year. That's more than 1 sports car or 1 ton of carbon being put into the atmosphere for every man, woman, and child living on Earth today. When we burn fossil fuels and clear forests, carbon dioxide is released into the atmosphere, but only half of that carbon stays in the atmosphere, warming our planet and contributing to climate change. The other half is removed from the air by our planet's ecosystems and ocean. And the big question is, in the future, as the carbon dioxide builds up, will the land and the ocean continue to take up that 50%? Or will they get saturated? Will they get too full and quit at some point? Or will they always just keep absorbing more and more CO2? In some regions, forests are releasing more carbon than they're storing. Forests gain carbon as they grow, and they release it as they die and decompose. And processes like drought, pests, fire, and deforestation contribute to the release of carbon. Ocean water, just like the vegetation on land, absorbs carbon dioxide from fossil fuel emissions. Doing so, however, changes the chemistry of seawater with wide-ranging impacts on marine ecosystems. And as surface water in the ocean continues to warm, carbon absorption will slow down at some point. Models of atmospheric CO2 help us understand what our satellites see, so we get a more complete picture of this global carbon cycle. We can check our models against atmospheric observations, and if they look reasonable, then we have confidence in using these models to predict how carbon is going to change in the future. The United States is utilizing our unique science capabilities to increase our understanding of our home planet, improve lives, and safeguard our future. Now, let's talk a little bit about temperature. Everything that we have done in the past decade, everything that you've done, has something in common. It all took place during the hottest decade ever recorded since humans began keeping temperature records about 150 years ago. Since 1880, this Earth's temperature, our temperature, has risen about 1.5 degrees, and scientists predict that it's going to rise even more, and already we can see some signs, like global sea level, which rose over an inch during the last decade, almost twice as fast as the average during the 20th century. Arctic summer sea ice declined about 300,000 square miles, enough ice to cover the states of Texas and Kentucky. The vast majority of climate scientists say evidence for human-caused warming is clear, but less is understood exactly how this warming will change our complex interactions between our planet's land, water, sky, and the living organisms that inhabit our world. As scientists improve their understanding and predictions about climate change, satellites provide critical data about what's happening on our planet today. These are real-life observations scientists use to improve their predictions. And we have a global view of the three major pieces of the climate puzzle. 1. How much of the sun's energy is actually hitting the Earth? 2. How much of that energy is reflected back into space? And 3. How much of it is being trapped and heating our planet? Satellites measure the sun's energy, which fluctuates in a 10 to 12-year cycle. Now, could increased solar activity be causing global warming? Well, satellite evidence shows that the solar cycle has only a slight impact on our planet's temperatures. In fact, even though the last few years have been some of the warmest on record, the sun has been in a deep lull in activity. That means slightly less solar energy is actually reaching the Earth. And when the solar cycle ramps up again, scientists expect temperatures will rise even a little more. The second piece of this temperature puzzle is our planet's brightness. Now, all other things being equal, a more brighter, more reflective planet bounces more energy back into space. Some of the brightest, most reflective areas of our planet are those covered with ice. And imagery shows those areas shrinking, especially in the Arctic. As sea ice vanishes into darker ocean, our planet becomes less reflective and warms even further. Clouds also reflect a lot of sunlight. As our planet warms, more water vapor evaporates, potentially creating more clouds. More cloud cover increases the Earth's brightness, possibly helping to cool the planet. But clouds and the small particles called aerosols that help them form are climate wildcards. And many current climate models predict some cooling due to the increased cloud cover. But will it be enough to significantly slow global warming? Scientists are still using data to look for that answer. Further complicating this issue is that water vapor is actually the world's most abundant greenhouse gas. That's right. The same molecules that might cool our planet in cloud form actually warms it when they're in the form of a gas. And they help create a blanket around the Earth, catching heat radiating from the planet's surface and trapping it within the atmosphere. And as the planet warms, more water vapor evaporates from the ocean, creating more of this heat-trapping greenhouse gas. And we humans can't control the amount of water vapor in the air, but we have a much greater impact on the other major greenhouse gases. Carbon dioxide is the second most prevalent greenhouse gas, and it's our biggest contribution to global warming. Fossil fuel burning releases large amounts of carbon dioxide into the air, and satellite instruments capture the infrared signature of carbon dioxide in the global atmosphere. And they show a rise throughout the past decade. Scientists also monitor other greenhouse gases such as methane, nitrous oxides, and CFCs, chlorofluorocarbons. In recent years, CFCs have decreased, where methane and nitrous oxide are on the increase. Greenhouse gas is most likely the main contributor to current global warming. It's the key piece in the temperature puzzle, and it's unlocked the door to higher and higher temperatures. Now, let's take a look at some of the real-life observations as evidence. This graph, based on air samples contained in ice cores and direct measurements, provides evidence that atmospheric CO2 has increased since the Industrial Revolution. The Earth's climate has changed throughout history. Just in the last 650,000 years, there have been 7 cycles of glacial advance and retreat, with an abrupt end of the last ice age about 7,000 years ago, marking the beginning of our modern climate era and of human civilization. And most of these climate changes are attributed to very small variations in Earth's orbit that change the amount of solar energy our planet receives. The current warming trend is of particular significance because most of it is very likely human-induced, and proceeding at a rate that is unprecedented in the past 1,300 years. Ice cores drawn from Greenland, Antarctica, and tropical mountain glaciers show that Earth's climate responds to changes in greenhouse gas levels. They also show that in the past, large changes in climate have happened very quickly, geologically speaking, in tens of years, not millions or even thousands. Sea level rise. Global sea level rose about 7 inches in the last century, and the rate in the last decade, however, is nearly double that of the last century. Sea level rise is caused primarily by two factors related to global warming. One, the added water from melting land ice, and two, the expansion of seawater as it warms. And this first chart tracks the change in sea level since 1993 as observed by satellites. And the second chart, derived from coastal tide gauge data, show how much sea level changed from about 1870 to 2000. Global temperature rise. All three major global surface temperature reconstructions show that Earth has warmed since 1880. And most of this warming has occurred since the 1970s, with the 20 warmest years having occurred since 1981, and with all of the 10 warmest years occurring in the past 12. Even though the 2000s witnessed a solar output decline, resulting in an unusually deep solar minimum in 2007 and 2009, surface temperatures continue to increase. And this graph illustrates the change in global surface temperature relative to the 1951 to 1980 average temperatures. The 10 warmest years in the 134-year record all have occurred since 2000, with the exception of 1998. And 2014 ranks as the warmest year on record. Now, November 2015, the combined average temperature over global land and ocean surfaces for November 2015 was the highest for that month in the 136-year period of record, at 1.75 degrees Fahrenheit above the 20th century average. This topped the previous record of 2013, and it also marks the 7th consecutive month that a monthly global temperature record has been broken. This video time series shows the 5-year average variation of global surface temperatures from 1884 to 2014. The dark blue color indicates cooler than average areas, and the dark red indicates areas warmer than average. Warming oceans. The oceans have absorbed much of this increased heat that we're talking about, with the top 2,300 feet of the ocean water warming up about 1/3 of a degree Fahrenheit since 1969. Glacial retreat. Glaciers are retreating almost everywhere around the world, including the Alps, Himalayas, Andes, the Rockies, Alaska, and Africa. Shrinking ice sheets. Data from satellites show that the land ice sheets in both Antarctica and Greenland are losing mass. The continent of Antarctica has been losing about 134 billion metric tons of ice per year since 2002. And Antarctica has lost about 36 cubic miles of ice between 2002 and 2005. And Greenland's ice sheet has been losing an estimated almost 300 billion metric tons per year. Greenland lost 36 to 60 cubic miles of ice per year between 2002 in 2006. Both the extent and thickness of Arctic sea ice has declined rapidly over the last several decades. Arctic sea ice reaches its minimum each September. So September Arctic sea ice is now declining at a rate of about 13% per decade, relative to the 1981-2010 average. And this graph shows the average monthly Arctic sea ice extent in September since 1979, derived from our satellite observations. The 2012 sea ice extent is the lowest in the satellite record. Extreme weather events. The number of record high temperature events in the United States has been increasing, while the number of record low temperature events have been decreasing since 1950. The United States has also witnessed increasing numbers of intense rainfall events. Ocean acidification. Since the beginning of the Industrial Revolution, the acidity of surface ocean waters has increased about 30%, and this increase is the result of humans emitting more carbon dioxide into the atmosphere, and hence more being absorbed into the oceans. The amount of carbon dioxide absorbed by the upper layer of the oceans is increasing by about 2 billion tons per year. Climate change alters ocean chemistry, leading to ocean acidification. Much of the carbon dioxide that enters the atmosphere dissolves into the ocean. In fact, the oceans have absorbed about 1/3 of the carbon dioxide produced from human activities since 1800, and about half of the carbon dioxide produced by burning fossil fuels. And as carbon dioxide in the ocean increases, ocean pH decreases or becomes more acidic, and this is called ocean acidification. With ocean acidification, corals cannot absorb the calcium carbonate they need to maintain their skeletons, and the stony skeletons that support corals and reefs will dissolve. The ocean's pH from 8.179 to a current pH of 8.069 means the ocean is about 30% more acidic now than it was in 1751. And if nothing is done to reduce the carbon dioxide emissions into the atmosphere, ocean acidification will increase and more corals will be damaged or destroyed. Decreased snow cover. Satellite observations reveal that the amount of spring snow covering the northern hemisphere has decreased over the past 5 decades, and that the snow is melting earlier. Now, we live in a greenhouse, essentially. Life on Earth depends on energy coming from the sun. About half of the light reaching the Earth's atmosphere passes through the air and clouds to our surface, where it's absorbed and then radiated upward in the form of infrared heat. And about 90% of this heat is then absorbed by the greenhouse gases and radiated back towards the surface, which is warmed to a life-supporting average of about 59 degrees Fahrenheit. Greenhouse gas emissions from our homes and commercial buildings come from fossil fuel combustion for heating and cooking needs, management of waste and wastewater, and leaks from refrigerants in homes and businesses. Indirect emissions from electricity use by our homes and businesses have increased due to increasing electricity consumption for lighting, heating, air conditioning, and appliances. And in this graph, we see that in 2013, direct greenhouse gas emissions from homes and commercial buildings accounted for approximately 12% of total U.S. greenhouse gas emissions. Residential and commercial activities contribute to greenhouse gas emissions in a variety of ways. 1. Combustion of natural gas and petroleum products for heating and cooking emits carbon dioxide, methane, and nitrous oxide. Emissions from natural gas consumption represents about 81% of the direct fossil fuel CO2 emissions from our homes and commercial buildings. 2. Organic waste sent to landfills emits methane and contributes to greenhouse gas emission levels. 3. Wastewater treatment plants emit methane and nitrous oxide. 4. Fluorinated gases, mainly hydrofluorocarbons, HFCs, used in air conditioning and refrigerant systems, can be released from servicing or from leaking equipment. We can reduce greenhouse gas emissions from our homes and commercial buildings by reducing energy use through energy efficiency. Our homes and our buildings use large amounts of energy for heating, cooling, lighting, and other functions. Green building techniques and home energy improvements can allow new and existing buildings to use less energy to accomplish the same functions, leading to fewer greenhouse gas emissions. Techniques to improve building energy efficiency include better insulation and air sealing, more energy-efficient heating, cooling, ventilation, and refrigeration systems, efficient lighting, passive heating and lighting to take advantage of the sunlight, and the purchase of energy-efficient appliances and electronics. There are many things we can do at home to help reduce greenhouse gases and save money. Change 5 lights. Replace 5 of the most frequently used light fixtures, or the light bulbs within them, with energy-efficient ones, and we will help the environment while saving about $70 a year on our home's energy bills. Energy-efficient lighting provides bright, warm light, generates less heat, uses less energy than standard lighting, and lasts 10 to 50 times longer. Heat and cool smartly. Heating and cooling accounts for almost half of a home's energy bill. And there's a lot we can do to drive down this cost. Simple steps like changing air filters regularly, properly using a programmable thermostat, hiring a home inspector as part of a routine home maintenance plan, and having your heating and cooling equipment maintained annually by a licensed contractor. All can save energy and increase comfort while helping to protect the environment. Air seal and insulate our homes. Reduce air leaks and stop drafts by using sealant, weather stripping, and insulation to seal a home's envelope and add more insulation to the attic to block out heat and cold. We can save up to 20% on heating and cooling costs and significantly enhance our home's comfort with comprehensive air sealing and insulating measures. Reduce, reuse, and recycle. Reducing, reusing, and recycling in our homes help conserve energy and reduces pollution and greenhouse gas emissions. Composting our food and yard waste also reduces the amount of garbage that we send to those landfills and reduces greenhouse gas emissions. Use water efficiently. It takes lots of energy to pump, treat, and heat water, so saving water reduces greenhouse gas emissions. Saving water around the house is very simple. 3% of our nation's energy is used to pump and treat water, so conserving water conserves energy that reduces greenhouse gas pollution. Try some simple water-saving actions such as not letting the water run while shaving or brushing your teeth. And save money while conserving water by using water-efficient products. And did you know about 10% of all US homes have leaks that waste 90 gallons or more per day? So go fix those water leaks. Running a dishwasher only with a full load can save about $50 and about 100 pounds of carbon dioxide every year. Hire a certified home energy inspector. A home energy inspection helps homeowners determine where their house is losing energy and money and how such problems can be corrected to make the home more comfortable and energy efficient. A professional home energy inspector, sometimes called an energy auditor, can provide a homeowner with a list of recommended energy-saving home improvements, many of which you can do yourself. A home energy inspection may include checking for air leaks, examining the insulation, inspecting the furnace and ductwork, and using an infrared camera. A home that leaks energy costs a lot of money to operate. So how do you stop it from leaking and wasting energy? It starts with a certified home energy inspection. A home energy inspection includes a certified professional inspector checking the systems and components of a home to find out where a house could be more energy efficient. And the end goal is to save energy and save money and make a house more comfortable. Installing energy efficient lighting and appliances will help. So will creating a sealed barrier around the house, which is like putting a blanket around the outside and minimizing the air leaks. Upgrading a home to save energy can save anywhere from 5 to 30% of the home's energy bill. To get a thorough home energy inspection, contact your local certified professional inspector, certified by the International Association of Certified Home Inspectors. During the inspection, the inspector may start outside, looking for problems around walls, windows, and doors. If there's a big opening, the home is losing energy and money. Next, the inspector may head up to the attic to check for leaks on the top of the home's barrier. That attic access could be a problem, letting conditioned air escape from the house. A big part of a home energy inspection is determining how well the insulation insulates. Insulation should be correctly installed in between all areas of the house frame. That means it needs to be evenly applied and not just jammed into spaces. The energy inspector may check the holes where electrical lines pass through. If they're not sealed, they're leaking energy. Then it's down to the basement. The furnace and water heater could be wasting energy. The inspector will check the furnace's energy efficiency rating. Furnaces generally lose efficiency as they get older, and it could cost more to keep an old furnace running than to replace it with a new one. And maybe all that's needed is a new air filter. Some people haven't changed their filter for months, even years. That gunk clogging the filter means the furnace has to work harder and use more energy to heat the house. If the water heater is old, it may not be efficient, and if it's not insulated well, it's also losing energy. Now it's on to the ductwork. The inspector will look for connections to make sure that they're not leaking. Ductwork has to be sealed to keep the conditioned air going where it's supposed to go. If the screwdriver can go in the hole, it means one thing for sure, that money is leaking out. The inspector may close all the windows and doors and anything else that lets outside air in, and then turn on exhaust fans to depressurize the home. And the idea is to suck air out of the house, allowing outside air to leak into the home through openings. And with the windows and doors closed and a fan running, air leakage may be indicated using an infrared camera. In the winter, the inspector may scan the interior of the home looking for cold air coming in. And here, the darker the color, the worse it is. These black spots mean big air leakage. So, a certified home energy inspection can reveal the ways that energy escapes a home, which costs a homeowner money. The home energy inspection report will provide the homeowner a list of home energy improvements that are most energy efficient and cost effective. Just like a home is a system of interdependent parts, where one part may affect many others, the Earth too is a system. And Earth system science is the study of how scientific data stemming from various fields of research, such as the atmosphere, the ocean, land ice, and others, fit together to form the current picture of our changing climate. Climate change is one of the most complex issues facing us today. It involves many dimensions: science, economics, society, politics, and moral and ethical questions. It's a big global problem felt on local scales that will be around for decades and centuries to come. Carbon dioxide, the heat-trapping gas that has driven recent global warming, lingers in our atmosphere for hundreds of years, and the planet, especially the oceans, they take a while to respond to the warming. So even if we stopped emitting all greenhouse gases today, global warming and climate change will continue to affect future generations. In this way, humanity is committed to some level of climate change. Now, how much climate change? That will be determined by how our emissions continue, and also exactly how our climate system responds to those emissions. And despite increasing awareness of climate change, our emissions of greenhouse gases continue on a relentless rise. In 2013, the daily level of carbon dioxide in the atmosphere surpassed 400 parts per million for the first time in human history. The last time levels were that high was about 3 to 5 million years ago during the Pliocene era. Because our homes and buildings are responsible for a large proportion of greenhouse gas emissions, climate change deserves special consideration by all homeowners. While new homes can be designed from the ground up with energy efficiency in mind, existing homes typically offer many opportunities for improvement. To help enhance the energy efficiency of homes, home inspectors can encourage homeowners to perform home energy inspections and implement the recommended measures. These improvements can be a cost-effective way to provide significant energy savings to homeowners, as well as improve the health, comfort, and safety of our homes. And we have found that energy inspections alone do not produce energy savings. A key strategy is to empower all homeowners all over the world with the right information to make smart decisions about home energy efficiency. I hope you've learned a little about climate change, greenhouse gas emissions, and what we can do to save home energy. Tell family and friends that energy efficiency is good for their homes and for our planet. Find a local certified home inspector. Visit inspectorseek.com.